Hello, this is Erica Golston. Today we'll be talking about Lab 4, which has to do with biomagnets. All right, so for a table of contents, we'll do an introduction on the experiment, the physics concepts and models that are studied in this experiment, the actual procedure that was conducted. Then we'll go through the code used to generate a computational model and discuss our results and then draw some conclusions based on those results. All right, so for a brief introduction, the purpose of this lab is to study magnetic fields of a bar magnet, and those are going to be the fields on and off axis with the magnet. And we'll also be comparing observed and predicted values regarding magnetic fields and their magnitudes. The physics principles involved are, of course, the concept of magnetic fields, which relates to magnetic dipoles, and then mathematically, the Biot-Savart law, which is what we use to describe the behavior of magnetic fields that we observe. All right, so let's look at the physics concepts and models that are covered. The biggest thing here, of course, is going to be the property of magnets. So magnetism is generated by the movement of charged particles in a material, and every material contains electrons which have intrinsic spins that creates a tiny magnetic dipole. So when these dipoles align in a material, they create magnetic fields that can interact with each other, they can interact with objects, they can interact with other fields such as electric fields. And then to tie everything together, the Biot-Savart law is the mathematical model that describes the behavior of magnetic fields. And it states that the strength or magnitude of a magnetic field will be inversely proportional to the distance away from the field. All right, so let's look at the experiment and see if what we observe matches with that mathematical description. So we set up our experiment by orienting our phone with the magnetometer in it orthogonal to the magnetic field of the Earth. That way, the magnetic field of the Earth would not interfere with the readings and values that we calculated. And then we located the magnetometer chip and made sure that it was on the axis with the bar magnet through aligning it with a meter stick that was on the axis. So we measured the distance exactly by a meter stick and calculated our values. And this is what we got. So we got to see that relationship directly, that as the distance r from the magnet increased from 0.138 meters to 0.298, the magnetic field decreased by about a magnitude of 10, about one whole order of magnitude, from 2 to the negative 4, or times 10 to the negative 4 rather, than to 2 to the negative 10 to the negative 5 Teslas. Yeah. So as you can see, that's a pretty quick decrease in strength, pretty rapid. And when we graph this logarithmically, the graph of the natural logs of the magnitude versus of the distance has a negative slope, which also shows that inversely proportional relationship. So when we look at the actual mathematical models that we can use to calculate these, the magnetic field of the bar can be calculated as K, some constant, times distance R to the N. And those numbers can be derived directly from the graph of our observed values. So when we plug and chug the numbers, we can use these to calculate the magnetic dipole moment of the bar magnet, which when we got our constant K, 4.71 times 10 to the negative 7, we got the dipole moment mu as about 2.36 amperes times meter squared. So this was a pretty nice depiction of the behavior that we observed as the magnetic field decreased in strength with the distance. And then when we look at the off-field data, we get the same thing. We see that as the distance increases, the magnitude of the magnetic field decreases. And then we also see another thing described in the Biot-Savart law, which is that the on-axis field is about twice as strong as the off-axis field. So we can see that at the average perpendicular distance of 0.193, the net field was about 5 times 10 to the negative 5 Teslas, which is about half of what we saw when we were measuring on the axis. So this once again supports our mathematical models. Now to look at the computational model that we used. All right, so we use GlowScript and Python to generate this model of our bar magnet and magnetic fields around it. So we can see the magnet right here, the small gray dot, and then the magnetic fields around it are represented by arrows. So we've got the on-axis fields, which is the arrows in orange here, and then the off-axis perpendicular fields, which are in cyan, which we can see are visibly smaller in size, representing that they're smaller in magnitude compared to the field that's on the axis with the bar magnet. And so we can look at the code to the right that was used to develop this model, where we established our constants and created the bar magnet depiction. We defined our magnetic field function over here with dipole B, and then we set the observation locations. And then this all was to create the arrows representing the magnetic fields, establishing those with the arrow scale and their distances, all using a distance of 1. And then on this last section here, we calculated the experimental values that were used in the actual experiment conducted, which we can see that the on-axis magnetic field at a distance of 1 was exactly 4.71 times 10 to the negative 7, which is our value of K that we got earlier. So pretty cool to see how the math that we did with just the numbers and the computational model lines up together when we've got that same magnetic dipole moment. And we can see that our overall distance, not the perpendicular, but the diagonal distance, was 0.2729, as we showed earlier in the earlier data. And we got the value of the magnetic field at 45 degrees at distance d. So that was nicely generated by our computational model. All right, so let's discuss our results. So altogether, these all support the mathematical models that we use to describe the magnetic fields and the different relationships that are involved with that. So we can see from the experimental results that the strength of the magnetic field does vary inversely proportionally with distance. And we can also see that the on-axis field should be about twice as strong as the off-axis field. So all of this is represented by our data. And then from the slope of the graph, we also got to confirm another part of Biot-Savart's law, which is that the inverse proportion is cubic. So we've got that the strength of the magnitude is proportional to the inverse of the cubed distance. So those were all supported by the experimental results, which is a good representation of our mathematical models. All right, so some sources of error involved could have been environmental effects, such as other electric or magnetic fields in the area, which our equations were unable to account for. Then, of course, the equipment, if the magnetometer's precise exact location was unable to be determined, because it could have been off by, a couple millimeters, something like that. And then also the oversimplification of the assumptions made where we modeled the bar magnet as a single magnetic dipole instead of that overall distribution. So all those could have led to small amounts of error, but we still got to see that the relationships predicted by the models still held true in our results. All right, and let's look at some conclusions. If we hadn't oriented the experiment to compensate for magnetic north, then we would have seen interference with our results by the magnetic field of the Earth. So, as stated earlier, we had to orient the meter stick specifically in a way that the magnetic field of the Earth could be neglected because it was not affecting the magnetic field of the magnet. And then lastly, if we were to stick two identical magnets together, we would just see the strength of the magnetic field or the magnitude double, but the direction would remain unchanged because the dipole overall would still point in the exact same direction. All right, so thank you, and I hope this was educational.